nanohub.org.
Online simulation and more for nanotechnology.
Welcome everyone to our new installment of our series on machine learning for material science. Today, it's my pleasure to welcome Dr. Anand Chandrasekaran from Schrödinger. Anand joined Schrödinger in 2019, and he's currently a product manager of material science informatics. He graduated from the group of Nicola Marsari at the Swiss Federal Institute of Technology in Lausanne, Switzerland, with a PhD in material science. And before joining Schrödinger, he worked in the group of Professor Rampi Rampasand on a number of topics, including polymer informatics and machine learning, force fields. And we look forward to hearing what Anand has to tell us today. Thank you, Anand.
Thank you, Alejandro, for the wonderful introduction. I'm really grateful to be here. All right, let me get started. So my name is Anand Chandra, and I'm the product manager of material science informatics at Schrödinger. So today's webinar is going to be about how we can use machine learning in material science, especially in combination with physics-based simulations. And I'm going to explain how we do this within the Schrödinger platform, both in terms of our software that we have and also in terms of the scientific case studies that we've done within the company as well. So Schrödinger is a computational chemistry and a computational material science company, and we are more than 30 years old right now, and we have a lot of expertise in physics-based simulations, and by that I mean quantum mechanical simulations for gas-phase molecules using a tool called Jaguar, which performs really fast calculations for large molecules in the gas phase. And also we have a quantum mechanics GUI for Quantum Espresso for doing quantum mechanical calculations for solid-state systems and interfaces. And we also have a number of molecular dynamics workflows based on our MD engine, Desmond, which allows you to do GPU-powered molecular dynamics of a large variety of systems, such as polymers and organic molecules and formulations and micelles and higher-level coarse-grained simulations as well. So in addition to the physics-based simulations, we also have a variety of machine learning tools that interface with our physics-based simulations. And we have an enterprise informatics solution called Live Design, where it's basically a collaborative platform for companies to bring together physics-based simulations, machine learning, data visualization, and analytics, and coming up with new ideas and new molecules for drug discovery, or new molecules or new polymers for materials design. So having a collaborative enterprise informatics platform really supercharges designing new materials using computational tools. So as I said, the main focus of today's webinar is going to be using machine learning in material science. And why do we want to use machine learning in material science? So if you look at some of the main challenges in material science, for example, coming up with an energy efficient lithium-ion battery, or coming up with a catalyst for ammonia synthesis, or for example, let's say coming up with a new biodegradable polymer, these are extremely challenging tasks for material science. And in order to come up with a new material that has satisfied these criteria using experiments, it takes of the order of a few months or a few years. And if we use physics-based simulations to go through and do high-throughput simulations to scan through these materials before synthesis, we can bring this down to of the order of few days or a few weeks, or a few days or a few weeks to do these physics-based simulations using MD or quantum mechanics. But with machine learning, if you couple machine learning with the right featureization technique and the right machine learning model that respects the physics-based origins of the system, then you can actually get property predictions in the order of few seconds, and you can scan through billions of materials to get the property of interest. So the main challenge in material science is to come up with the right featureization scheme for different types of materials. So when you're working with small molecules, you're looking at like 2D descriptors and binary fingerprints, topological descriptors, and graph-based convolutional neural networks, which are the current state-of-the-art approach for predictions of properties of molecules. But in addition to that, we can also generate quantum mechanical descriptors for these molecules like dipole moment, the quadrupole moment, the HOMO-LUMO values, and the band gap values. These descriptors can be generated using our physics-based workflows, automatically doing geometry optimization and things like that to automatically generate these physics-based descriptors. And we can add those featurization schemes to our small molecule machine learning systems as well. Similarly, for polymers, we can't just treat polymers as a molecule because we know that large molecular weight polymers have different types of physicochemical descriptors that are important to capture properties like the glass transition temperature or the dielectric constant, for example. And we've custom built these descriptors for polymers to improve the accuracy of machine learning models for polymers as well. And in some cases, machine learning may not be the right tool for polymers. For example, for copolymers or for polymer blends, in those cases, we can actually use our MD-based tools to get more accurate properties for these more complex systems, material systems. For periodic inorganic solids, for example, inorganic crystals, for ceramics, for metals, and for alloys, we know that we can't use the same types of RDKit type descriptors. We have a variety of other descriptors, for example, based on MatMiner or the SOAP descriptors, which can generate these descriptors from the 3D CIF files, and we can use those descriptors with a variety of different machine learning models to predict properties of solid state materials. Finally, for formulations and mixtures, sometimes you have a mixture of a variety of different molecules with different compositions. And for example, a polymer plus a molecule at different molecular weight ratios. And we need to generate descriptors for each of these individual components separately, and also take into account the composition of that particular material in the overall formulation. And that descriptor needs to be provided to the machine learning model. So all these tools can be used to make machine learning models for a variety of different materials. The most well-established tool that we have within Schrodinger to make machine learning models for molecules especially is called AutoQSAR. And AutoQSAR is a fully automated machine learning tool within our Maestro GUI platform solution, where you load a CSV file with a list of molecules. For example, you can load a CSV file with one column as a SMILE strings and the other column as a property values. And AutoQSAR, and you hit the button train, and AutoQSAR automatically generates all the descriptors and fingerprints. It removes unwanted fingerprints based on the Pearson correlation, and then it does a variety of different machine learning models depending on whether you want to do classification or regression. And it also does multiple train test splits, and it gives you a report saying that this is the top performing model. These are the top 10 performing models. Once you have these top 10 performing models, you can easily just draw a new molecule and make a prediction for that particular molecule. So one example here is shown here for AutoQSAR for ionic liquids. So we downloaded this data set of 392 ionic liquids from the NIST Thermo database. And this 392 ionic liquids have associated electrical conductivity value. And here you can see these are actually two molecules, not a single molecule, but AutoQSAR is able to handle this particular format as well. It's just two molecules separate, the SMILE strings of two molecules separated by a dot. And we can load this into Maestro. We can visualize a 3D structure if we want to, and we can create machine learning models for these type of molecules. And in addition to the list of the top performing models that you see here, AutoQSAR also has a visualization scheme here. For example, the red parts of the molecule, the fluorine atoms here are contributing to an increase in the electrical conductivity, whereas the blue parts of the molecule here are contributing to a decrease in the electrical conductivity. So this type of feedback of the machine learning models on the atomic contributions really helps us design new chemistry and understand what's going on and what types of substructures are more important for what properties. But recently, so AutoQSAR is quite old. It's a very mature technology that works for small data sets for anywhere from 30 molecules to 5,000 molecules. But more recently, we've developed a tool called Deep AutoQSAR, where we've incorporated all the latest and greatest deep learning methods based on neural networks. For example, dense neural networks, also tree-based models like random forest regressor, XGBoost, and variety of other models, transformer and graph convolution based models into this particular tool called DeepAutoQSAR. And we know how difficult it is to train these deep neural networks. We have to be very careful about hyperparameter optimization and also look at different types of how do we counteract overfitting and things like that. So all these processes are completely automated using DeepAutoQSAR. So DeepAutoQSAR will output the 5 best models with the automatically optimized hyperparameters for a particular neural network architecture. And you can use those 5 best models to also get an uncertainty estimate, a standard deviation across the 5 predictions. So this will give you a rough estimate of how uncertain your machine learning model is in terms of the confidence of the machine learning model. Because we do know that we have to be careful that machine learning models can be quite bad at extrapolation. So having at least some measure of uncertainty, either based on the similarity or based on the standard deviation, would be useful to see how confident we can be about our machine learning model. So a quick comparison of, I'm going to compare how AutoQSAR versus DeepAutoQSAR using a particular case study here. So this data set was actually generated by a colleague of mine, Garvit Agrawal, in Schrodinger. And this is the data set of 1,400 homobenzylic ethers. And these molecules were used as potential candidates for redox flow batteries. And one of the criteria for redox flow battery is the oxidation potential. So we wanted to create a model for the oxidation potentials for this class of materials so that we can screen a more number of molecules using the machine learning model as opposed to using DFT. So we collected this data set from a CSV file and loaded it into Maestro and ran AutoQSAR and DeepAutoQSAR. And we can see here that traditional AutoQSAR, which has more traditional methods like kernel partial least square regression or multiple linear, in this case, the best model was the multilinear regression model. The R-square was around 0.94. In the case of DeepAutoQSAR, which is the best model, was a neural network with a test R-square of 0.98. So we see that based on internal case studies, we see that once you have more than around 500 data points, there's a strong likelihood that a deep learning approach is going to benefit your particular application. And with DeepAutoQSAR, you can actually train it on a GPU to make the training even more faster. So this model was trained for 4 hours on a GPU to get this particular performance. So in addition to so both AutoQSAR and DeepAutoQSAR are based on the SMILE strings and 2D featureization schemes. But we know that for many cases and for many materials classes, those 2D featureization techniques is not sufficient. So we can actually generate more types of descriptors. For example, we have a molecular materials descriptor panel, which can generate organometallic descriptors for different metal centers. You can specify the metal center and it can calculate properties like the buried volume, the bite angle and cone angle of those organometallic systems, optimized with DFT level accuracy. We also, if you want a faster descriptor, we can actually calculate certain descriptors using semi-empirical approaches. For example, if you want a quick estimate of the dipole moment or the HOMO-LUMO value using MOPAC, you can get this using this panel. And if you want a full DFT calculation to get DFT level accurate descriptors, taking into account the geometry optimization and other steps in the DFT workflow, you can run Jaguar to get DFT descriptors. And once you have all these different descriptors, you can actually add them to AutoQSAR or DeepAutoQSAR as additional descriptors and run machine learning model for that particular property. Similarly, for inorganic systems, you can actually generate some inorganic descriptors. For example, all these element descriptors, oxidation state descriptors, and structure descriptors are actually MATMiner based descriptors that we've inbuilt in the backend, and we can go directly from a CIF file to the MATMiner descriptors. We have some intercalation descriptors that are specific to lithium-ion cathode materials that take into account the environment around a lithium-ion solid-state system. And these descriptors can be used for example, training a machine learning model for lithium-ion cathode materials. And we can also use SOAP descriptors. And we know that SOAP descriptor stands for smooth overlap of atomic positions. This is a rotationally and translationally invariant way to generate 3D environment descriptors for molecules and materials. But the problem with SOAP descriptors is that it results in thousands of columns because it's an extremely sparse basis set representation. So we can do dimensionality reduction with principal component analysis And you can say, for example, generate SOAP descriptors with 10 PCA components, and it would generate that and save those 10 PCA components into the project table in Maestro, and those descriptors can be used in machine learning. So I'll be giving an example of how we use these solid state descriptors in a case study that I'll show in a few slides. And finally, for example, for polymer materials, we have a specific panel that can generate polymer fingerprints and polymer descriptors. And to go into more detail about these polymer fingerprints and polymer descriptors, this slide demonstrates how we can improve the accuracy of models by taking into account specific descriptors that have been tailor-made for polymers. For example, we loaded around 315 polymers from the Pisarano Polymer Handbook with glass transition temperature values. And if we load these data sets into AutoQS R and train a machine learning model, we get a root mean square error of around 38 Kelvin for the prediction of the glass transition temperature error. However, if we provide some custom polymer fingerprints, for example, we provided topological torsion fingerprints for these polymer repeat units, and these topological torsion fingerprints were actually normalized with respect to the repeat unit. So as the polymer repeat unit becomes bigger, your fingerprints don't change, because we are dealing with large molecular weight polymers here, and your polymer property should be invariant to the repeat unit representation. So we normalize the topological torsion fingerprints with respect to the repeat unit. We also put in some additional descriptors like the length of the side chain and the backbone, for example, and the number of fused ring atoms, which change the polymer chain stiffness. And once we do that, we can actually bring down the root mean square error considerably from 38 Kelvin to around 11 Kelvin. So these descriptors can be generated very easily using our tool. So I'd like to give another case study for machine learning for molecules. But in this case, the descriptors that we're going to be using here are actually going to be, in addition to 2D descriptors, are actually going to be obtained from molecular dynamics. So this example shows how we went about first extracting data sets for viscosity. So we went through literature values, we went through literature data sets carefully, and we selected organic molecules which were not charged. We removed any extreme values of viscosity and temperature, because we're trying to make a viscosity model to predict the viscosity of any molecule at any given temperature. And as you include more and more extreme data sets, like if you have an outlier at 1000 Kelvin, your machine learning model is not going to be great. And since we collected data set from multiple data sets from literature, in some cases there's a positive deviation of viscosity with respect to temperature, and this is because of mismatch from different literature sources. So we made sure to remove any positive deviations from, like, your viscosity should be decreasing with temperature for molecules in general. So we made sure to remove any positive deviations of viscosity or temperature, and make sure that the data sets was consistent. So this is the distribution of your viscosity, and this is the distribution of the temperature of the measurements in which the viscosity was made. Overall, we had more than 1,000 unique molecules with viscosity measurements, and the temperature ranges from 227 Kelvin to 404 Kelvin, and the viscosity ranges from 0.1 to 26 centipoise. So the goal is, can we create machine learning models for this particular property as a function of temperature? So we tried two different models. One is descriptor-based approach, which is more similar to the AutoQSAR approach, where we generated RDKit descriptors and Morgan fingerprints and also MATMiner descriptors for these molecules. And we provided these descriptors to a variety of different tree-based, not just tree-based, but also a variety of different machine learning algorithms like linear regression, tree-based regression, support vector regression, and multi-layer perceptron. And in addition to these RDKit Morgan and MATMiner descriptors, we also added in molecular dynamics descriptors as well to see if it improves the performance. I'll go into more detail about the molecular dynamics descriptor in the next slide as well. And we also have a graph neural network based approach where we don't provide any explicit descriptors. The molecule itself is a graph, and the atoms are nodes in the graph, and the bonds are edges in the graph. And we compared these two different approaches. So the MD descriptors that we generated were things like heat of vaporization, density, and the Hansen solubility parameters from MD, and the root mean square displacement. So we had a total of around 8 MD descriptors that we calculated from these amorphous systems of these molecules. And we plugged in these descriptors to the tree-based models and the graph-based models. And one very illustrative graph here is shown here in the bottom right. You can see that the dark green line is the graph-based model for viscosity, whereas the cyan line is the graph-based model with MD descriptors. And we see that adding MD descriptors really drops the root mean square error for predictions of viscosity, especially when you have low data set sizes of less than 500 molecules. And most of our customers, the biggest problem in material science, especially amongst our customers, is that they are dealing with small data set sizes. So having the power of really powerful descriptors from physics-based simulations can really reduce the amount of data that we need for machine learning. And we also looked at, using the Shapley feature analysis, we looked at the most important descriptors for viscosity. And we were able to show that, for example, the heat of vaporization obtained from MD was the most important descriptor for a viscosity, and it was positively correlated with viscosity as well. And we provided the inverse of temperature as a descriptor because the inverse of temperature has a more direct linear relationship with viscosity as opposed to the temperature. And we see that as you expect, as you increase the temperature, the viscosity goes down. And so using a combination of 2D descriptors or graph convolution approaches plus MD descriptors, it seems to be the best way to go forward in obtaining accurate machine learning models, especially at low data set sizes. So in this previous case study, I talked about how we obtain descriptors from molecular dynamics. Similarly, we can actually obtain descriptors using DFT. So one particular case study here is we obtained a database, this database of optical properties of organic chromophores, of organic compounds. So these organic compounds and their optical properties are extremely relevant for photovoltaic applications and also for OLED devices. So this excellent paper had this dataset source of around 20,000 measurements. So the measurements of around 7,000 chromophores in 365 different solvents. And these are the different properties that were provided in the publication. Properties like the molecular weight, the absorption wavelength, the fluorescent wavelength, the quantum yield, the absorption bandwidth, etc. And these authors actually used a graph convolutional based approach to combine the chromophore and the solvent and to make the particular prediction. And these are the different types of solvents that were used in this particular database. So the approach that we took was slightly different. We actually generated the 2D descriptors and DFT descriptors for the chromophore, and we concatenated it with the 2D descriptors of the solvent, and we provided those combined descriptors to the machine learning model. And we provided it to a list of machine learning models like multi-layer perceptron or XGBoost and random forest, etc. And we automatically select the best performing model for a particular property. So the Deep4Chem is the one that was published in literature. The blue line is MaxIML, which is our internal benchmark, a Schrodinger machine learning model. And the orange line is orange bar is the Schrodinger machine learning model with DFT descriptors. And for most cases, we see that adding DFT descriptors is an improvement in producing a reduction in the root mean square error for most of the properties. So we can actually look at what are the most important descriptors for these optical properties. For example, for the maximum wavelength of absorption, this is the property that we're trying to target. This is the experimental property. The most important property was the scale band gap, which we calculated with DFT. And the second most important property was the lambda max absorption that we calculated with DFT. So this is not surprising at all that these highly customized DFT descriptors are actually the ones that are most important for these optical properties. So this is a very strong, shows you how powerful physics-based descriptors can be in calculating these optical properties. The next case study I'd like to talk about is machine learning for the volatility of organic molecules. So volatility is something that's extremely difficult to calculate using physics-based simulations. And that's one of the reasons why we want to calculate volatility with machine learning. And we collected a data set of around 1,100 organic molecules and more than 12,000 experimental measurements. So the volatility of these molecules was measured at different pressures. So what was the boiling point of this molecule at a given pressure? And the pressure ranges from 1 torr to 30 atmosphere. So a huge range of pressures. And this could be for a variety of different applications. For ALD and CVD, it could be at one pressure range. For volatile organic compounds, you may be interested at a lower pressure range. So we want to make a model that can predict the boiling point of these molecules at any pressure. So we took this data set from literature. We scanned through data set from literature, and we had more than 200 chemical descriptors and 1,000 Morgan fingerprints for each molecule. So more than 1,200 descriptors. And we also provided the logarithm of pressure as an additional descriptor to the machine learning model, because we know that there's a linear relationship between the logarithm of pressure and the inverse of temperature because of the Clausius-Clapeyron rule. So we want to provide this physics-based intuition to the machine learning model. So we trained a model for this data set of more than 12K compounds, 12K experimental data points. And the highest performing machine learning model was the multi-layer perceptron, which resulted in a root mean square error of around plus or minus 2 degrees Celsius for the boiling point of these organic molecules. And the light gradient boosting machine did not perform as well. It was around plus or minus 8 degrees Celsius. And to our knowledge, this is one of the most comprehensive models of boiling points at different pressures for such a huge chemical space that's available out there in literature. And we looked at how well this machine learning model extrapolates. For example, these four molecules are extremely diverse, and they were not part of the training set of this particular model. And you can see here that the dots represent the experimental measurements for the volatility of these four different molecules, and the dashed line represents the machine learning prediction. And you can see the machine learning model is able to accurately predict the volatility of these compounds, and it's also able to extrapolate to higher temperatures as well. So we had to be very careful about choosing the right model. For example, if you had chosen a tree-based model, this extrapolation to higher temperatures may not have been possible because of the architecture of a tree-based model. So once we have this model is available within the software, and it can be used for a variety of different applications, ranging from atomic layer deposition and chemical vapor deposition. Although we focus on organic molecules in this particular case study, we also have a separate model that has the volatility of organometallic systems. So that's these two separate models have been trained, one for organic and one for organometallic as well. So both of these models can be used for a huge range of applications. So as I mentioned earlier, I'd like to give an example of how we can use machine learning for inorganic 3D crystals, for inorganic systems, for ceramics. So we downloaded a data set of 3,000 periodic structures for transparent conducting oxides containing indium, aluminum, gallium, and oxygen. So this data set was obtained from the NOMAD database from the Kaggle Challenge. And we wanted to create a machine learning model to predict the band gap of these inorganic systems using DeepAutoQSAR. So DeepAutoQSAR, by default, it has featureization schemes for molecules. So we need to manually generate the descriptors using the periodic descriptors panel. So we generated the element descriptors, oxidation state descriptors, and structure descriptors from the MatMiner package. And we also generated SOAP descriptors, which can capture the 3D environment around each of the atoms and provide a generalized 3D numeric value for a particular structure. And once we did that, we provided these descriptors to DeepAutoQSAR, and we trained a model. So this is how the system looks like in our Maestro user interface. And these two models here show that we are able to get a pretty accurate model to predict the band gap of these class of systems using 139 MatMiner descriptor. The R square is around 0.88. And with 139 MatMiner descriptors plus the SOAP PCA descriptors, we're able to improve the R square from 0.88 to around 0.94. So by really combining the appropriate descriptors for the appropriate chemical space, we're able to improve the performance of the machine learning model. So many of the case studies I showed earlier are machine learning models that are trained within Schrodinger. And these machine learning models are actually available within the machine learning property prediction panel in Maestro. So the user can for example, draw a molecule or an organometallic molecule, and they can predict the boiling point of these molecules at any given pressure. Similarly, they can predict the glass transition temperature of a homopolymer using the machine learning model. And we also have the frequency-dependent dielectric constant and dielectric loss of different polymers as a machine learning model. And finally, recently, we also added a machine learning model to predict the density of molecular liquids and also the viscosity of molecular liquids as well. So finally, we are currently working on a machine learning for formulations panel where you for example, in many cases, for example, for an electrolyte system or for a consumer packaged goods system, for consumer packaged good product, you actually have a mixture of different molecules like the active ingredient, a fragrance ingredient, or an additive, and you want to make a machine learning model for the entire formulation as a whole and not for an individual molecule. So in this case, we are designing a user interface where the user can upload a CSV file of where each row is a formulation, and the formulation actually contains different molecules at different compositions. And we are trying to map this to a particular property. So the formulation machine learning panel will automatically generate descriptors for each individual molecule, and it would also take into account the composition of that molecule in the formulation and make predictions for that formulation. And once we do this, we also want to identify what are the most important features for a particular formulation, which ingredient was the most important in affecting a particular property. And we also want to be able to use these machine learning models to synthesize new formulations or come up with new chemistries and new compositions. So this particular functionality for formulation machine learning is scheduled for a release early next year. So I think I give a brief, I mentioned how we want to come up with new formulations. Until now, I've been mainly talking about supervised machine learning, where we are going from the featureization to the machine learning model to predict the property, But sometimes we want to come up with a new molecule or completely new chemistry automatically. For example, here's an example where we use active learning to design new optoelectronic materials. So to design a new OLED molecule, you may want to increase your oxidation potential or reduce your reduction potential. And also, for example, choose a particular target value for a HOMO value. So how do we do multiple parameter optimization for these molecules? So we can actually select these criteria and provide a big pool of molecules to active learning. So with active learning, what we do is we provide a large pool of candidates. And for example, we can provide 1 million molecules. And instead of performing DFT calculations on 1 million molecules, what you would do is actually select 50 molecules from this candidate pool of molecules, calculate DFT using our DFT workflow, for example, the HOMO value or the reduction potential or the whole reorganization energy. And you would train a machine learning model on these 50 different molecules. And with the help of these machine learning models, you're going to make a query on the remaining candidate of molecules. So you take the next 10 best molecules that has been suggested by machine learning and again perform DFT and append the newly calculated properties to the training set. So using this process, we can actually go through the process of selecting the right molecules in a minimum amount of time. So instead of doing DFT calculations on a million molecules basically searching for a needle in a haystack, with active learning, you can actually within 200 or 300 calculations, you can go towards a target property of interest. But for active learning, we do need a large pool of candidate molecules. But in some cases, you do not have a large pool of candidate molecules. You just have an initial data set of 50 molecules, and you want to come up with new ideas for new chemistry. So in this particular case, genetic optimization is a very powerful technique. For example, here we trained the AutoQSAR model for the delta EST value. This is a experimental value for the energy difference between the singlet and triplet state for optoelectronic molecules. And we trained the AutoQSAR model for this particular property. And we want to minimize this delta EST value to 0 for this optoelectronic application. So we can actually load all these molecules into the genetic optimization panel. So we have an initial population of around 249 molecules. And we choose that we want to minimize the delta EST value calculated using AutoQSAR. And we ask the genetic optimization to randomly mutate these fragments to come up with new ideas for new chemistries that minimize this particular value. And so this is the red histogram here shows the distribution of the optoelectronic properties or distribution of the delta EST values of the training set. And the blue line shows the distribution of the delta EST values of the generated molecules. So we can see here the genetic optimization is quite effective in generating compounds of delta EST value closer to zero. Finally, I'd like to talk a bit about machine learning force fields. So this is another very interesting combination place where physics-based simulations and machine learning is combined. For example, here, the goal with the advantage of classical molecular dynamics is that it's extremely fast, whereas density functional theory is very slow and it only works for small systems. So if we can actually train machine learning models with DFT level accuracy, and we can use those potentials to do molecular dynamics with DFT level accuracy. So that's the main goal. But there are multiple challenges in getting this level of accuracy. First of all, we need to generate a huge compounds of millions or tens of millions of chemical space and generate DFT data set for this entire chemical space. And then we have to train a machine learning force field that works across a huge chemical space and that can actually be used for a stable molecular dynamic simulation. So we came up with the first generation of model, the SANI model, which is the Schrödinger-Ani model, which is based on the Ani family of neural network potentials. And it initially supported a coverage of 8 different elements. And the architecture is very similar to many of the Baylor-Paranello architecture that many of you would have known as. For example, you have a separate neural network for each element, and you calculate the energy contributions from each atom in your system, and you sum up the energy contributions to calculate the total energy of the system. And of course, this was trained to DFT level energies. But the problem with this first generation of these neural network model is that it neglects long range effects. It doesn't predict any charge, or it doesn't have any empirical charge correction as well. So we came up with a new architecture called QRNN, which is an upgrade on the SANI architecture. It also recursively predicts the charges on the atoms and equilibrates it during the prediction process. And we are predicting not only the energy, but also the energies, the forces, and we are training on the energies, forces, and also the charges. And once you're able to predict charges on the atoms, we can actually use empirical dispersion correction, and we can calculate the Coulomb interaction and add those contributions to the energy of the system. And with this approach, we're able to perform machine learning force field simulations on lithium-ion battery materials, for example. When you have a lithium-ion cation and an electrolyte, these systems are quite complex and they are charged. So having a charge recursive neural network is something it's extremely important for these type of properties. So as an example here, we simulated the bulk properties of certain liquid electrolytes using our QRNN machine learning force field, and we compared it with OPLS and experimental data points. So here are some of the properties that we calculated: density, specific heat of vaporization, viscosity, and the diffusion coefficient. And we noticed that the machine learning force field actually outperforms OPLS especially for properties such as the diffusivity and viscosity. So this is a really, it's extremely difficult to train these machine learning force fields because of the quantity of data that you need. But within Schrödinger, we're going to make this functional. So we're going to allow. These force fields are actually going to be available soon within the software, and eventually by later next year, we plan to have a solution where the user can actually fine-tune these models for a particular chemical space and run machine learning force fields for a particular chemical space. Finally, I'd like to wrap up about my talk here about talking about a bit about our enterprise informatics solution called LiveDesign. So LiveDesign is a browser-based enterprise informatics platform where you can combine experimental data, computational modeling, and informatics and visualization. So in a global organization, you have all these different aspects and all these different teams working on different aspects of the same problem, and having them able to collaborate seamlessly and share data and share workflows is something that's really powerful. So if a data analyst has trained a machine learning model and wants to deploy this machine learning model to the rest of the company, to the experimentalists, for example, this machine learning model can be very easily shared using this browser-based platform. Similarly, if a computational modeler has designed a workflow, an MD workflow to analyze a particular molecule or a particular class of molecules, this MD workflow can be shared with the entire company. So the user can just hit run instead of having to look into the details of a particular modeling workflow. So initially, LiveDesign was primarily for drug-like molecules, whereas now LiveDesign has been extended to polymers and copolymers and organometallics. And we are even able to load experimental data and visualize experimental data in LiveDesign and share these classes of materials like formulations, for example. You can run a formulation experiment experimentally and load into LiveDesign and train a machine learning model and share that machine learning model to come up with new formulations as well. So in summary, using a customized featureization approach that takes into account the physics of the system is something really important to develop the physics machine learning models for materials. And Schrödinger has a variety of high throughput physics-based modeling techniques based on QM and MD that really helps us to generate these descriptors to take machine learning to the next level. And we've demonstrated that machine learning can be applied successfully to a huge range of material systems, ranging from molecules to polymers to organometallics. And with LiveDesign, which is a web-based platform, we can actually deploy these machine learning models and physics-based workflows and actually collaborate on designing new materials. And finally, we also have machine learning force fields that have been trained with DFT level accuracy so that it can do MD simulations that would otherwise not have been possible. With that, I'll be happy to take any questions.
Thank you very much, Anand. This was a terrific presentation. There was lots of discussion on the chat and Q&A and back and forths. So let me ask a few questions. And let's start with the following. There's a series of questions about fingerprints. So first of all, just to make sure we're on the same page, what are fingerprints in machine learning? And can you tell us about your sense of the value of adding DFT fingerprints, given that they're costly, right? So how do I decide? Do I need do I need to spend the time doing DFT, or I can just avoid it?
So let me answer the first part of the question about fingerprints. So here, the fingerprints are basically substructures that if that particular substructure is present, that particular bit, so you have a vector of say 1024 columns, and one particular column, if a particular substructure is present, then that particular column is switched from 0 to 1. So it tells you basically if a particular substructure, for example, like a sulfur double bond benzene ring attachment is present or not. And how these fingerprints are calculated is it can be different, but one of the most common ones is called a circular fingerprint, where you draw a circle around an atom and see if that substructure is present in other atoms, and if that substructure is present, that particular column that is associated with the substructure is switched on from 0 to 1. So that's basically a fingerprint, and it's very cheap to calculate, but as you can see, it's based on the 2D structure. And for the second part of the question about DFT descriptors, yes, for most cases, actually, DFT descriptors may not be required, but for certain cases, like for example, for the optical properties cases, where your the optical property measured experimentally depends on the excited state properties and things like that. And in those cases, DFT descriptors is potentially useful, and that's why we focus on optical properties there. And yes, DFT is definitely expensive, but certain DFT properties are cheaper. For example, HOMO-LUMO values are fairly cheap, especially with Jaguar. Our quantum mechanics solution is pretty fast. Other excited state properties with DFT are obviously much more expensive. And if you want to avoid DFT, I can think of a few strategies. One is using semi-empirical descriptors like MOPAC and XTB. These semi-empirical descriptors are quite fast, not as fast as 2D, but they're definitely much faster than DFT. For a molecule, it takes a few seconds or a minute or so to get these semi-empirical descriptors. And with semi-empirical descriptors, you can get HOMO-LUMO values, polarizability, molecular hardness, and things like that. So those descriptors could potentially be useful if you want to avoid the expensive nature of DFT. And finally, we're also looking into transfer models where we are, like for example, for the optical properties, we are trying to predict the DFT descriptors and then predict so multi-fidelity or transfer learning, where the machine learning has seen the DFT descriptors, but then it's able to predict the DFT descriptors and use that as input for the experimental property. So those are different strategies to avoid calculating descriptors with DFT. Yeah.
And our experience is very much problem dependent, right? It depends how much data you have. So that's related to another question. Someone was saying, well, how do you do so well with only 300 data points? And this person was surprised at the accuracy. So maybe you can comment on that, on how the amount of data and the quality of the descriptors affect the accuracy of a predictive model.
Sure. For 300 data points, for example, AutoQSAR can handle it quite well. And the reason is that it focuses on machine learning models such as kernel partial least square regression or multilinear regression. So these models are not designed to handle tons of data. They're actually designed for small data sets. And so they work quite well for small data sets compared to neural networks, for example. Similarly, Gaussian process regression is something we've used for small data sets for polymers. Gaussian process regression is also something that works reasonably well for small data set sizes. And in addition to Gaussian process regression, the additional benefit of Gaussian process regression is that you get the uncertainty as well. And someone asked, I think I saw a question if an ensemble is used. And yes, we do use ensembles for most cases. Like when we make for example, in the final slide, I showed you a model for delta EAST AutoQSAR, and that is actually an ensemble of all the top 10 models that AutoQSAR has used. And definitely using an ensemble is really helpful when you're dealing with small data set sizes. So we do that. We do that for AutoQSAR and deep AutoQSAR. So I think for small data set sizes, using an ensemble and using machine learning models that are not neural networks is going to be really helpful. Yeah.
Very good. So maybe we have time for one more quick question and answer. So the question and a related follow-up is, how do you make sure deep AutoQSAR doesn't overfit? And potentially related, how do you automatically optimize hyperparameters?
So the way we benchmark deep AutoQSAR is through fivefold cross-validation metrics. So for example, when we, for example, this particular slide here, which shows deep AutoQSAR performance, this is actually on the holdout set. The test that is a test set that the deep AutoQSAR has never seen before. And we just do a random split 80%, 20 or 90%, 10%, and the 10% is completely kept apart. And within the 90% training set, we do fivefold cross-validation, and we select the best model based on the fivefold cross-validation. And of course, we also use an ensemble approach where we take not just one model, but we take the top top five models with different architectures and things like that. So yeah, the overfitting is reduced by looking at the cross-validation metrics rather than the training metrics itself. We don't want we're not looking at the training metrics. We're looking at the cross-validation metrics.
Very good. All right. Well, let's thank Anand again for a terrific presentation. Thanks, everyone.
Thank you, everyone, for attending, and thanks NanoHub for this opportunity.